Okay, so I've had a couple of students who have contacted me to ask about how to calculate chi-square. And chi-square is a lot different than the statistics that we have been doing when we were doing t-tests and ANOVA. And so it's a pretty big shift from the kind of calculation you were doing before. So I'm not going to do the full steps of hypothesis testing here where we identify our critical value and stuff. I'm just going to focus on how we do that calculation for chi-square. So the example that I have, we have a sample of 50 students classified as to whether or not they voted in the last election and with their academic status. So whether they're freshman, sophomore, junior, senior. So we see that 4 freshmen did vote, 6 did not. And we can kind of see a trend here that the more advanced a student gets, the more likely they are to have voted, right? So we see that only 4 of 10 voted as freshmen, but 13 of 15 voted as seniors. So we can kind of visualize that there might be an association here. We might think that there is between class rank and the likelihood of voting. And so we might find that this is statistically significant. I always like to look at the data and think about the data and make some predictions based on what I can see in terms of the patterns of my frequencies. So for chi-square, the first step is to find the expected frequency for each cell. Because if you recall, the formula for chi-square is the expected frequency minus the observed frequency, or the observed frequency minus the expected frequency. So we have the observed frequencies here. That's what we collected. That's what our data shows us. And now we're going to calculate for each cell the expected frequency. The first thing that I like to do is to go through and give each cell a designation. So I'm just going to go A, B, C, D, E, F, G, H. So now I can keep track of them. I know where they are. And so my calculation for that first cell, 4, for the cell right here, those who were freshmen who voted, the formula is the row total multiplied by the column total divided by the n. So my row total for A is 10. So I come over here and I grab 10. My column total for A is 32. So I go across my row and I go down my column and I grab those two numbers. Now my total n here is 50. So divided by 50. So I have 320 divided by 50 is equal to 6.4. That is my expected frequency for cell A. What that means is that that's what I would expect to be the value in here if there was no variation or no association between these two variables. So what chi-square is doing is it's saying, what's the difference between what we found and what we expected to see, and then measuring the size of that difference overall. So the last step in the calculation is to sum all of those variations or those differences. So we'll keep going. FE for B, so B is freshmen who did not vote, would be, again, 10, right? So the cell is here, but we're going to get the row total and the column total, which this time is 18, right, down here, divided by 50. So we have 180 divided by 50, which is 3.6. FE for C, and we're going to continue this process. C is this cell right here. 15 is the row total, 32 is the column total, so 15 multiplied by 32 divided by 50, and I don't know that one off the top of my head. Some of the others were easy, right, when multiplying it by 10, but that is 9.6. For D, it's equal to, so here's our cell D, our row total is 15, our column total is 18. And we multiply by 50, and that is 5.4. Shift my page up a little bit so we have enough space for all of our calculations. Let's see if I can do that and still have you see where these numbers are coming from. So E, this is cell E. The row total here is 10. The column total for E is 32. Divided by 50. All of them are divided by 50. That's the total N for everything. So what just happened? Well, our row totals and our column totals are repeating themselves, right? And you can kind of tell that's going to happen because you have 10 and 15 here and 10 and 15 here. So in this case, it doesn't always happen. But in this case, we're going to see some of that. So F is 2, right? That's that cell. But we don't want that cell. We want the total for that row. So we've got 10 again. Our column total is 18 underneath there. Divided by 50 is equal to 3.6. For G, we have our row total is 15. Our column total is 32. Divided by 50 is equal to 9.6. And for FEH, our row total is 15. Our column total is 18. Divided by 50 is equal to 5.4. Okay, so that is the calculation of FE. Those are our expected frequencies if there was no association between these two variables. The next piece of what you do, and I created a table because I wanted it to be clean, is you fill in your table. So the formula for chi-square, and I'm going to put it down here so you can see, chi-square is equal to the sum of, sorry about my summation symbol there, FO minus FE squared, whoopsie, I made my things too big, divided by FE. So, excuse me, I'm gonna do that over because you need to see it cleanly, is equal to the sum of, I did it again. I made my squigglies too high. FO minus FE over FE. Okay, so what we're going to do is we're going to take each observed frequency. That's the number from our chart over here, right? What we observed, that's our FEs, our FOs, minus our FEs, which we calculated over here for each cell. And we're going to square that value, and then we're going to divide it by this expected frequency. Okay? So I do these things in tables. It makes it so much easier for me to keep track of. So my FOs, I just go down the list. So I'll go ahead and label these A, B, C, D, E, F, G, H. And so we have 4, 6, 7, 8, 8, 2, 13, and 2. Those just come from this table over here. So H is 2, F is 2, D is 8. You can see that. Our FEs are what we calculated over here. So our FE for A is 6.4. Our FE for B was 3.6. Our FE for C is 9.6, and we continue to go down the list. 5.4, 6.4, 3.6, 9.6, and 5.4. Yes, these repeat. That's only because these column totals repeated, so don't assume that that's going to be true in every single chi-square you calculate. It won't be, okay? The next column tells us we are going to take our FO and subtract it from FE. So 4 minus 6.4 is minus 2.4. 6 minus 3.6 is plus 2.4. 7 minus 9.6 is minus 2.6. 8, positive 2.6. Do you see a pattern? Up and down, up and down. So our FE is essentially pulling what would be the expected frequency, and our variations are tracking up and down in a balanced way. Do you remember how we did the variations around the mean calculation, and when you added all those variations together, they equaled 0? This is a similar idea. So we have 8 minus 6.4 is 1.6. 2 minus 3.6 is negative 1.6. 13 minus 9.6 is 3.4. and 12. I'm sorry, not 12. That should be a 2. Sorry about that. 2 minus 5.4 is negative 3.4. So you can see how those balance each other out. Now we're going to take each one of these right here, right, our FOs minus our FEs, and we're going to square that value. So what does squaring it do? It gets rid of the negative, because a negative times a negative is a positive. So we, in the same way that we did with standard deviation, we're trying to get rid of that negative. Remember, our variations around the mean balance each other out and equal 0. So we square them. And then when we're calculating standard deviation, remember, we took the square root in order to get something that we could interpret. We're not going to do that here. We don't have that same interpretation issue, but the process is similar and the mathematical thinking is similar. So FO minus FE squared, 2.4 squared is, what is 2.4 squared? 5.76. And we have it again. And 2.6 squared is 6.76. 1.6 squared is 2.56. 3.4 squared is 11.56. Okay. Now, this is where most students mess up in the calculation of chi-square, is in this section here. You are going to be dividing by FE. So you're going over to this column again, not this one. Don't go over here. Stay here. So we are going to have 5.76 divided by 6.4. So I'm just going to write that in small if I can, so that you know where that number is coming from. So this one is 0.9. So make sure that you are coming over to your FE column to do those divisions in this step. As I said, this is where we have mistakes. People are going to the wrong column. That's what I do sometimes too, to grab it. So 5.76 divided by 3.6 is 1.6. 6.76 divided by 9.6 is 0.7. 6.76 divided by 5.4 is 1.25. 2.56 divided by 6.4 is 0.4. 2.56 divided by 3.6 is 0.71. 11.56 divided by 9.6 is 1.20. And 11.56 divided by 5.4 is 2.14. Okay, so chi-square, if chi-square is equal to, come back down here, the sum of FO minus FE squared divided by FE, and this column right here is FO minus FE squared divided by FE, then all we are going to do is we are going to sum this column. And when we sum this column, add all of these numbers together, we are going to get chi-square. That is our chi-square value. So if we add 0.9, 1.6, 0.7, 1.25, 0.4, 0.71, 1.2, and 2.14, we get 8.9. And that is our chi-square value. Now, if we were doing the 6 steps of hypothesis testing, we would go back and we would compare it to our critical value, finding our degrees of freedom, looking it up on the chart, finding our critical value, and then comparing our chi-square value that we computed to the critical cutoff value that was set in the tables. It will be statistically significant. I can ruin that for you if you don't like spoilers. So this one would be statistically significant. So we had a hunch when we looked at the data that it probably was, because we saw a pattern that we had a larger proportion, not just the number, but a larger proportion of students who voted compared to those who didn't vote as they went up in class status. So as you move from freshman to sophomore to junior to senior, we kind of see that pattern. So when we ask the question, is voting behavior independent of academic status, right? That would be our null hypothesis, right? They're not associated, they're independent of each other. So if we were running through this process, we would reject our null and we would say that voting behavior is dependent on academic status, okay? Or that there is an association between voting behavior and academic status based on the data that we collected. I hope that running through this hand calculation example is helpful to you, and we'll kind of explain some of the intricacies of how we calculate chi-square and what the logic is, the mathematical logic behind why we do it that way.